Okay, that should be fine. Okay, and we're live. No, just let me click. That's okay. Just 1 minute. Got it. And click. And now you should be able to click back.
But
what can you click back?
this is not my screen.
Yeah.
This is like Yosef's screen.
No, that's this laptop screen, which is
Okay.
what's up there. But if you click backwards, so you're controlling this.
Yeah.
So you're broadcasting from this online to that and then to that.
No.
Okay, that's moved over.
Yeah, so there'll be a tiny lag.
Yeah,
Click back and forth.
That's not so bad.
line above with all the.
Yeah, we will.
all the other guys.
Oh, yeah, we got it. Thank you.
Yeah, perfect.
Masaki.
But then, can,
Me,
okay.
They're showing the projector the Zoom screen.
it's perfect.
I think we're good enough to go.
Okay, so welcome everybody to the final talk of the first week of this conference week, in which we will be very happy to have Emil Martinec from Chicago telling us about symmetric products, strings, and ADS3 CFT2.
Thank you, David. And thank you to the organizers for the opportunity to speak at Black Hole Microstructure 4. Apparently they didn't learn their lesson in versions 1 through 3, so here I am again. And talking actually about mostly about two things that I talked about in two previous editions, namely this work that our postdoc in Chicago, Bruno Balthazar, reported on a year ago, as well as work done with Stefano and David 2 years ago. But we didn't really mine all of the information we could get out of this previously, so I thought I would sort of give a kind of a broad brush view of things that we've been doing over the last few years, trying to weave it together into a coherent story. So what's the general structure? Well, up in a lot of places, in particular, they've been useful in thinking about black holes in ADS3 CFT2. You know, part of a lot of the effort that's been reported in this conference is about understanding microstate geometries that realize particular BPS microstates in this symmetric orbifold, which, because they're BPS, they can be transported from one region in the moduli space to another and studied both in the conformal field theory and in gravity. So today we're going to explore a couple of aspects of this. One is string perturbation theory around particular microstates that we can handle not just at the level of supergravity, but at the level of perturbative string theory. And we'll also ask the question whether symmetric products always describe black holes, whether the symmetric product that people usually work with is whether that structure of, you know, long twist sectors is always indicative of black hole behavior, or whether it can be something else. So before we get started in all of this, I want to remind people of some particular aspects of string theory on ADS3 cross S3 cross, say, T4 or K3. We'll be working mostly with T4, but keep K3 in mind. So we're compactifying type 2B string theory on T4 times a circle. And we'll be wrapping 1 branes and 5 branes around that circle. And so if we think about the U-duality group of the T4 part of the compactification, that has a U-duality group, which is 055 with integer coefficients. And that duality symmetry is broken by the fact that we have a large number of 1 branes and 5 branes in the background. And so we ask, what is the sort of residual, or if you like, the little group of this charge vector that, you know, it moves you around in the background, but keeping the charge vector fixed? It's not the full 055Z. And so what that means is that elements of O55Z that don't keep the background fixed map you around to different regions in the moduli space. And so in particular, they can map, you can either think of them as mapping you around in the moduli space, keeping the charge vector fixed, or you can think of them as holding the charge, the moduli fixed and mapping around the charge vector. Two ways of thinking about the same thing. Thinking about it in the latter way, you realize that the only thing that the duality group needs to preserve is the symplectic inner product of this charge vector, which is n1 times n5. So the U-duality group keeps that symplectic inner product fixed, but can move you around to different regimes, which have the interpretation of different numbers of 1 branes and 5 branes, but with the same product. And so there's one cusp in the moduli space, which has the charge assignment n comma 1, but then there are other cusps which have the charge assignments n5, n1, or n1, n5, or 1n. They're all different regimes in the moduli space. The regime where supergravity applies is over here, where both charges are macroscopic. But the symmetric orbifold lives in this cusp of the moduli space where the charge assignments are n strings and 1 5 brane. And things up here are not very gravity-like. In particular, if you ask, what is, say, the ADS radius of curvature in units of the string scale, the ADS radius of curvature is the string scale. So supergravity sort of maximally doesn't apply. And in fact, we've heard a number of times in a number of talks, in particular in Yiming Chen's talk, there's a phenomenon that goes on called the Horwitz-Polkinski correspondence transition that says that something which might be a black hole in regimes where the curvature is very weak becomes something very stringy and merges into a perturbative string spectrum when the curvature is large in string units.
Sorry, just one question.
Yeah.
If I stay in the region where supergravity holds, should I also keep n large? It's just like because it's just stringing a strong coupling, then I don't need to take the number of branes to be large. So because
you should think of so string perturbation theory is in powers of the dilaton. The dilaton moves around in the moduli space. Up here, it's basically n. So 1 over n is the natural expansion of correlation functions in the symmetric orbifold, and that's an expansion in powers of 1 over g string squared. Out here, the dilaton, if you're, say, in the F1 NS5 duality frame, the dilaton is like n5 over n1. So if you want to work at, say, fixed 5 brane charge, then you're considering some number of strings, which is, again, macroscopic. But the dilaton is a little bit bigger than it is in this cusp by a factor of n5 squared. Okay. And we're typically going to be in that regime where we want to consider, roughly speaking, the number of 5 branes as being fixed, and the number of 1 branes you should think of as being roughly 1 over g string squared.
Thanks.
Now, when thinking about fundamental strings bound to NS5 branes, there's a phenomenon of charge fractionation, which is maybe most easily thought of by thinking about type 2A NS5 branes and taking the lift to M theory, where a fundamental string in type 2A lifts to an M2 brane that's wrapped around the extra circle of M theory. But when such a string encounters a stack of M5 branes, it can split because M2 branes can end on M5 branes. And so a fundamental string, which is wrapping this vertical direction, can split into N5 separate strips. And of course, each strip looks like, from the point of view of somebody sitting in the remaining 10 dimensions, as an effective string. But the tension of that effective string is N5 times smaller than the tension of the fundamental string. And this will be an important ingredient in our story. And one of the things the questions that I'm going to be asking persistently in this talk is the question of how can we see this fractionation from the point of view of thinking about string theory in the dimensionally reduced theory in 10 dimensions. And largely those efforts to find, well, so the effort to find that fractionation of a factor of n5 in excitations will be successful in some cases and unsuccessful in others. Okay. Now, why is this fractionation important? It's important for thinking about the entropy of the generic black hole microstates. So if we think about the BTZ entropy, it goes like square root of n5 n1 times the square root of the number of momentum and anti-momentum excitations. At least one can write it this way as a, well, this is basically the Cardy formula for the CFT2. But that expression for the non-extremal entropy of the system has an extension to this system of 5 branes carrying fundamental strings bound to them. And so if we sort of back off a little bit from the ADS3 limit and talk about just the decoupling limit of 5 branes, then the non-extremal BTZ entropy formula has a non-extremal black 5-brane entropy formula. And there's a natural interpretation of that, a non-extremal 5-brane entropy in terms of what are called little strings, namely that this idea that sitting inside the 5 branes are these non-abelian little strings that have a tension that is fractionated by a factor of n5. And so if we just compute the Hagedorn entropy of a gas, a Hagedorn gas of such strings with fractionated tension, then it turns out that that reproduces the black 5-brane entropy, at least in qualitative terms. And the way you should think about it is you start with a bunch of strings that are winding one way and some anti-winding strings, and you let them start interacting, and eventually they just become some soup of a highly excited string. And this is the entropy of that string, at least in qualitative terms. So if that's the sort of hand-wavy explanation of the black 5-brane entropy, then we should be able to recover the BTZ entropy as a particular limit of that entropy formula. So if we just think a little bit about the relation between the oscillator excitation levels of a Hagedorn string and its energy, there's a contribution from the 0 modes of the string, namely its momentum and winding. And we want to work in the following regime. We want to work in this regime where we interpret the string tension in this formula as being the tension of the little string, okay, which is n5 times smaller than the tension of the fundamental string. We are also constrained by asking the system to carry a net momentum. And then because the strings are fractionated, n5 times the net winding of the fundamental strings in the background. Basically, this is just a statement, you know, that I split the string into n5 strips. Okay, if the fundamental string was winding this direction w times, then the little strips have a total winding which is n5 times w. Okay, and so if I make that series of assumptions, and I take the following low energy limit, so take the energy of the gas of strings to 0. Take the length of the circle that the strings are wrapping to size to go to infinity, but holding the product fixed. That's the ADS3 decoupling limit. And so you can check if you take this formula, you plug it into the Hagedorn entropy formula that you just recover this expression. Basically, what you're doing is by taking Ry to infinity, you're making the energetic cost of the anti-winding strings to be very large. And so the system wants to just saturate on having as little string winding as possible, which is say n1 bar equal to 0 and n1 being what it's required to be by the super selection sector. Joseph.
Just a stupid question, make it completely go. Has anybody tried to do a Horwitz Polkinski game for the deepest strings on a 5 branes, you know, to try to go to the Hagedorn temperature to find the effective field and to play the Horwitz Polkinski game, but not in string theory, but rather in the S5 word volume? Somebody must have tried.
Well, basically the question you're asking is, can I find the little string somewhere in the world sheet theory on NS5 brains?
Or some effective field theory, some effective field which describes the condensate of the strings, that's only the strings, they have some, but to build a Horwitz solution, for example.
That is the question we'll be dancing around for the rest of this talk. Right. So note, by the way, I said there were these multiple cusps of the moduli space, one of which had the symmetric orbifold in it and had effectively only one 5' in it and a large number of winding strings. None of this fractionation phenomenon exists there, okay? Because there's only one 5', there's nothing to fractionate on. It's only in these other cusps where the effective string theory has N5 5' that you need to be looking for this fractionation phenomenon to explain the black hole entropy. Okay, so remember all of that, put it aside for the moment. I'm going to start talking about various microstates. The microstates I'll be concentrating on are the two-charge microstates, which were the subject of a number of talks already this week. Here they are in all of their ugliness. What are they characterized? As usual for BPS solutions, they're characterized by some set of harmonic forms and functions. And Lunin and Matur, in a very beautiful set of papers more than 20 years ago, gave an expression for all the metric coefficients and coefficients in all the other supergravity fields in terms of a set of Green's function integrals. So this is the natural Green's function in 4 Euclidean transverse dimensions. And then the different forms and functions get some source that gets integrated, convolved with that Green's function. Okay. And so what's important for us is that the shape of the 5 branes in the transverse space is governed by some particular source contour. If you specify a particular microstate by specifying a particular set of source contour functions, and if you think about doing a Fourier decomposition of this set of source functions, then there will be a set of Fourier mode amplitudes, and you should think of those mode amplitudes as specifying the expectation values of some number of integer quanta carried by the microstate. So here we are. The complete set of two-charge microstates can be characterized by those integer mode quanta, how many of them you have in each of 8 possible bosonic and 8 possible fermionic polarization states. Now what are these things? These are basically different states that the little string windings can be in. Okay. And if you want some more concrete way of thinking about it, you can take the NS5 F1 system and T-dualize it to the NS5 pieces. By T-duality on the circle that the strings are winding, then the string winding turns into momentum. And all you're thinking about is momentum modes that are carried by the 5 brane. That's the bound state, okay? So if I have a 5 brane, you just look at the fields that are carried by a 5 brane, and there are basically 8 physical modes that are bosons and 8 physical modes that are fermions. And each of those modes has a mode number, that's this P. And so you just have to tell me to specify a state, how many modes there are in each polarization state. And there, as I say, there are 8 bosonic and 8 fermionic. But reinterpreted in terms of supergravity, these 4 modes are specifying where the string is in its transfer, where the 5 brane is in its transverse space. These are some internal gauge multiplets on the 5 brane. And the subscript here saying what the mode number is in, after going to the NS5 F1 description, it's the net mode, the net winding, the net little string winding carried by this particular polarization. And of course, there's a conservation law that says that the total winding has to be N1, N5. So in general, that's some complicated looking thing like this. And so, if you can do this series, this Green's function integral, you can describe the supergravity fields. Even that is too complicated. So we will focus on some particular very special configuration space, which is tractable. And this is what one does all the time in this game. Generic black hole-like states are, some kind of complicated mess. And so one's always stuck between, you want genericity, but you want calculability. And those two tend to conflict with one another. So in order to be able to do calculations, we'll do simple things. So the simplest thing you can do is to focus on taking just one mode, the plus polarization state. So we'll have the string wiggling around in the 1-2 plane in some particular way. Sorry, the 5 brane is wiggling around in the 1-2 plane in some particular way. And so we'll just take that particular mode. We'll take it in bunches of k. So the kth excited mode, and then you want n over k copies of it. And it turns out that that particular configuration of the 5 brane admits an exact worldsheet description in string theory. This is based on original work done by Givon and Kudasov, not for black hole microstates, but they were thinking just about 5 branes separated in their transverse space. And so we sort of borrowed their ideology to adapt it to this configuration of 2 charged microstates. And the construction is basically to, when can you solve things on the worldsheet? When you have a lot of symmetry, like we just heard from Andrea. The nicest symmetry you can have is current algebra symmetries. So the nicest possible target space is a tensor product of group manifolds. So we're going to take a tensor product of group manifolds, which is basically R51 times SL2R times SU2. The SU2 is going to describe the angular sphere transverse to the 5 branes. The radial direction of the SL2R is going to describe the radial direction away from the 5 branes. And then this R51 is basically the directions along the 5 branes. Now you notice though that what I've described here is a 12-dimensional target space, right? 1, 2, plus 4 is 6, plus 3 is 12. So I have 2 dimensions too many to do string theory. So what can I do? I can get rid of 2 of them by gauging. And so a particular embedding of a U1 cross U1 isometry inside this group manifold describes this particular configuration. And that embedding of this group, so the U1 cross U1 are a pair of null isometries of this upstairs group G. For reasons I don't want to get into. And the one parameter I have in choosing the embedding of this U1 cross U1 into G is something that codes a particular property of the 5 brane source configuration, namely that the 5 brane is going to be spinning around in some circle in the 1-2 plane. What do I get to choose? I get to choose the pitch of this spiral of the source. And so, but that pitch is discrete because by the time I get to the periodicity of the Y circle, I have to periodically reconnect onto some 5 brane that's Ry times the distance Ry below it. And so I get a discrete pitch of this thing. And what that turns out to code is that the geometry that's sourced by this thing has a ZK orbifold point near the origin. And so what the geometry actually looks like is that as you go out radially in this ADS3, at very large radius, you basically have the geometry of this circle that the 5 branes are winding, and that's just some circle of a fixed radius we'll call Ry. And then as you come in, eventually at some point there's a cross stops being constant radius, but starts shrinking in the effective geometry of the gauge theory. And what you find is that in fact you have a cap in the geometry which is locally ADS3 with this ZK orbifold singularity at the bottom of it. And so in terms of quantum numbers that are carried by the system, all of these are BPS ground states. All the geometries I get by choosing this parameter K are BPS ground states of the system carrying 2 charges. In addition to the string winding charge and the 5 brane charge, in addition to carrying some angular momentum. And for k equals 1, you get the state which has the maximum possible angular momentum on the BPS bound. And then the subsequently larger values of k just get that maximum value divided by k equals 2 or 3 or 4, et cetera. So this sequence of models you get by increasing k steadily marches you in towards the state with j equals 0, which is the extremal BTZ black hole. So it's a very, it's nice in the sense that they're sort of black holes in the neighborhood. On the other hand, world sheet string theory is completely solvable in perturbation theory. Oh, and I should have said, this ADS3 limit is the limit of taking the size of this Y circle to infinity, as I said a few slides ago. Okay. So having this world sheet string theory, I should ask what it looks like. So what are the excitations around the vacuum? Now, vacuum here is not the vacuum of the space-time CFT. The vacuum here is the vacuum of perturbative string theory. I'm expanding around a particular geometry, okay, which is not global ADS3. It's ADS3 quotiented by some ZK symmetry. So what string theory computes for you is not perturbation theory around small excitations around global ADS. It's computing small excitations, small string excitations around this particular background. And that's why it's interesting. You're asking what is the spectrum of small excitations about something which has, as k gets larger and larger, an increasingly large redshift that more and more closely approximates an extremal black hole. So, all right. Well, there are some set of vertex operators. I'll go into a little more detail about what they look like in the next slide. But suffice it to say, there, as far as bosonic excitations, there are a nice. If I'm looking at, if I'm looking at the BPS line, among the vertex operators that I should be able to find are the ones that perturb me to nearby points on the BPS bound. So if I take a BPS state like this one, and I perturb it by a BPS vertex operator, I should get an infinitesimally different BPS state. So I should look for the maximally BPS vertex operators in this background. They should describe the deformations along the BPS bound. So as I was saying, those are basically string vertex operators that obey the BPS condition. And there are some that are Nova-Schwarz, Nova-Schwarz. There's some that are Ramon-Ramon. There's some that are Gravitino-like. So there are a bunch of them. And what you can do is you can then look at the quantum numbers of those vertex operators and try to match them to the enumeration of half BPS states that we gave here. And so what it turns out is that the Nova-Schwarz, Nova-Schwarz vertex operators precisely perturb you in this spectrum of excitations. The Ramon-Ramon ones perturb you in this spectrum of excitations, and the Gravitino ones add fermionic excitations. All right. So what are these vertex operators a little bit more explicitly? Well, they look like standard string vertex operators, as we saw in some earlier talks. What's a string vertex operator? It has some center of mass wave function, and then it has two oscillator excitations which carry the supergravity polarization state of the thing. Or if I'm looking in the Ramon sector, some spin field. Now, what I have to be doing is moving around in, remember this mode label was string winding. So some aspect of this string vertex operator is some kind of winding number along the Y circle. If you want to think about it in more conventional gravity terms, again, do T-duality on the Y circle, where this is just a standard graviton carrying momentum on the T-dual Y circle, but it's the same thing. Okay. And so I have to take this collection of vertex operators I can build this way. Because I'm doing a gauged Wess-Zumino-Witten model, I have to impose not just the standard Virasoro constraints that string vertex operators carry in perturbative string theory, but I also have these U1 cross U1 gauge degrees of freedom that I have to quotient out by. So there's an additional set of constraints that these vertex operators have to satisfy. But looking at the center of mass excitation, one sees an interesting structure that connects up to David Turton's talk earlier in the week. Namely, that if I look, so in order, I should say, in order for the state to be half BPS, the center of mass excitation has to be a highest weight state in the SU2 part and a highest weight state in the SL2 part. And so if I look at those wave functions and I look at them at large principal quantum number, then what's happening is the excitation is becoming more and more localized at large J near theta equals pi over 2 and R equals 0. And that's exactly the structure of this, the shock wave. If I could take J to infinity, this would be David's shock wave. But I can't take J to infinity in string theory. J is bounded. The unitary representations of this sort only appear for spins up to of order n5 over 2. And there's actually an intriguing phenomenon that every graviton wave function looking like this has a component of it which could be interpreted as a condensate of string winding. Except that, and this is the phenomenon that Andre was talking about in the previous talk, of an isomorphism of the winding 0 representations at spin J and the winding 1 representations at spin n5 over 2 minus J. So these are isomorphic as representations of affine SL2R conformal field theory, but they have two completely different interpretations. One has the interpretation in winding 0 as a graviton excitation, and the other has an interpretation of a string that's winding the azimuthal direction of ADS3. And what you see is that as you increase J, the graviton wave function gets increasingly localized in the center of ADS3, but the winding component expands out because its spin is becoming smaller and smaller. So they exactly trade places at J equals halfway up to the maximum. And for J larger than n5 over 4, the string winding wave function is getting enormous, and the graviton wave function is becoming David's shock wave. Question.
Sorry, it's true that I cannot crank up J up to above the unitary bound numbers and agree on. But what about the spectral representation state? So can I take arbitrary spectral flow and have perturbation with also?
Yeah, so there's some very subtle things going on in this theory that because the U1 that you're gauging on the world sheet to get the physical string involves the J3 of the SL2. The winding that Andrea is talking about is not orthogonal to the gauge space, and so you can shift Andrea's winding by doing large gauge transformations in the U1 that you're gauging. And so there are various subtleties with the representation theory that I don't want to go into, but suffice it to say, you can't evade this just by doing something simple. Okay. How am I doing on time?
About 20 minutes.
Okay, good. We're in good shape. All right. So that's half BPS. Half BPS deformation is completely understood. You tell me what nearby half BPS state you want to get to near the particular one that the background is describing, and I'll give you the collection of vertex operators you need to apply to the background to shift you there. Moreover, these are all 1-1 operators on the world sheet. So in some formal sense, you could take any one of these massless vertex operators and exponentiate it into the world sheet action. And that would describe a coherent state deformation of the round source background into an arbitrary nearby half BPS deformation. And if you could go arbitrarily far away, you would get the arbitrary half BPS ground state. Of course, going macroscopically far away, and that requires you to apply of order n such vertex operators, and that gets you outside the perturbative regime. But at least qualitatively, I think we understand fairly well the entire half BPS state space as something in perturbative string theory, modulo some issues that I'll
partition function or elliptic genus that counts them, some half BPS partition function.
yeah, these were all counted, ages ago.
Yeah.
It's partitions of n.
Yeah.
Well, it's a partitions of n with a decoration of 8 bosons and 8 fermions, so it's completely trivial. They're of order e to the root n1, n5 of those things. Okay. Okay, but if we can do half BPS deformations, we can do quarter BPS perturbations. What do those correspond to? They correspond to moving away from things that are highest weight in SU2 and in SL2. So, but only on one chirality of the world sheet. So we want to preserve half the supersymmetry, so we'll keep the right movers on the world sheet in their BPS ground state, and we'll make the left movers more generic. So we can do that, as I say, by going away from highest weight state on the left in SU2 and in SL2. In order to solve the gauge constraints, we need to turn on some momentum along the Y circle. So in particular, we need to be in the winding 0 sector of the string winding on the Y circle. And the null gauge constraints, the sort of axial version of axial component of the null gauge constraint acts on these quantum numbers and sets m plus n equals k times ny, where k was this parameter describing the orbifold singularity in ADS3. So if you want to see a FT interpretation of what these should correspond to, a natural guess is that I'm making, so if I take this k over to the other side, it looks like the y momentum that's carried by an individual perturbation here is 1 over k units times the integer quantization of momentum on the Y circle. So it looks like I'm exciting things by L minus 1 over k for this quantum number and j plus minus 1 over k for this quantum number. And that matches, that fits with some analysis of fractionated superstrata that we did quite a few years ago now, which I think serves to be, is due to be revisited, because what we actually described was only the states which had n equals 0 and m equals some funny number, which was basically like the maximum angular momentum that this strand could carry. And so I suspect there's a much larger fraction space of these things, which the world sheet is telling you should exist, and just haven't been found yet in supergravity. Things with larger, you might say, well, what about L minus 2 over k and L minus 3 over k? Yeah, those should be excitations on the string world sheet. You should be able to find them by taking the space-time stress tensor, which you can construct in this world sheet. It's something that was done by Yvonne Kudasov and Seidberg. So take the space-time stress tensor, act it on this vertex operator, find the space-time OPE of the two. You should be able to find all of the other excitations that are associated to the space-time super-Virasoro symmetry. But I'm telling you, these are the only ones that have supergravity analogs. All the rest of them are presumably quite stringy in nature. Right. I said everything here. Oh, yeah. So there are various other elaborations of the superstratum story that have been explored in recent years. Things called supercharged modes, things vector valued, things that are 60 vector modes. All of those you can get at by playing around with the gravity polarization state here. So for instance, I took my J's to be in SL2 here. Why can't I take J left to be in T4? Okay, that'll describe something whose dimensional reduction is a 6-dimensional vector. And okay, so there's more room to play. I suspect that in the end of the day, the list of things that one gets as supergravity perturbations will match nicely onto the things that you can do in superstrata. Okay. Right. But one thing I want to emphasize is that the finest modings are absent. The excitations have moding 1 over k, whereas if you check what is the strand length that you get by applying this vertex operator, it's 2j plus 1 times k, where j is the spin in SU2. And so, and 2j plus 1 is bounded by n5 because of this unitarity bound in the worldsheet affine current algebra. And so we're missing some finest fractionation that seems like perturbative string theory can't capture somehow. And my guess is that this might be because what we're looking at are perturbative string excitations and not this fractionated string that underlies the black hole sector of the theory. Okay. Let me just comment briefly that once we start playing this game, we can, of course, continue playing it and add in back the winding on the Y circle. As soon as we add winding on the Y circle, though, there's a level matching constraint in string theory because you have winding and momentum on the same circle. You have to have oscillators excited up to a level n times W. And so we have to excite oscillators on the left in order to get a consistent string perturbation. But then once we start adding oscillators on the left, it's no longer something that lives in supergravity. It's a string perturbation that's a quarter Bps, but it's not something you can identify as something that Nick will tell you how to condense. Okay. And still the finest oscillator, the finest fractionation is missing by a factor of n5. Okay. Let me talk just briefly about where I think this perturbative worldsheet description starts breaking down. And one place where it breaks down is when this profile that describes where the 5 branes are in their transverse space. If that profile, there are n5 5 branes that are wrapping this Y circle, and they're wiggling around in the transverse space. And in this depiction, the color coding is to tell you which 5 brane periodically reconnects to which next 5 brane. So, you know, red goes to yellow, goes to green, goes to blue, goes back to red, go around the color circle, you go around the set of periodic identifications in this figure. But the point I wanted to make is that as the thing wiggles around, any pair of these n5 5 branes might self-intersect. And so as I move around the half BPS configuration space, there are some special loci where a pair of 5 branes coincides. And what's going on geometrically is that in the Lunin-Matur geometry, this source profile codes a Kaluza-Klein monopole structure in the geometry that's sourced by the 5 branes. And what is a Kaluza-Klein monopole? It's something that's codimension 4, and in some codimension 4 locus, namely a line in 5 dimensions, 5 spatial dimensions. So along a line in 5, so this line is basically where this core of this KK monopole structure exists, where some circle that's fibered over the geometry collapses to 0. And so if I have a pair of 5 branes that are coming close to each other, this f of v, if this f of v is starting to self-intersect, the f of v is telling me where there's some circle in the geometry that's a 0 size and then grows and then goes back to 0 size. So there's some kind of S2 in the geometry. It's not a topological S2, but it's an S2 which reaches a minimal size at the place where these two source strands start to come together. And when they actually do coincide, there's an S2 which is just 0 size. And so I can ask, okay, what happens when I have an S2 that's vanishing? Well, you know, Strominger in the mid-90s said, wrap D branes around it, they become massless. And so there should be some kind of condensation phenomenon associated with the condensation of wrapped D branes. This is manifestly a place where string perturbation theory breaks down because I'm saying D branes are becoming massless. And so I should be able to pair produce D branes, and that's something that's way beyond string perturbation theory. But what are those things? We're in type 2b theory. There's an S2, we can wrap a D3 branes around it. So there's an additional leg. So the D3 brane is pinned to where the 5 branes are. And there's a pair of 5 branes that comes together. The 5 branes are wrapping the T4. And so the remaining leg of the D3 brane can wiggle along the T4. And the claim is this is the little string. This is the little string this is the little W string that goes massless when a pair of 5 grains coincide.
So what's the difference between these and the fractional D1 brains? Like I have some D3 brain wrapping a 2 cycle and some like orbital singularity, and I have a fractional D1.
Same sort of idea. If you want to pull that D1 brain off of the D3, you have to string a bunch of them together in order to get something that can escape onto a Coulomb branch. Same story here. These things should be able to turn into fundamental strings if you piece enough of them together to make a full string
And the
linkage.
difference on the S2, normally you need some difference on the S2 in order for them. You need some difference on the S2 in order for them to.
In order for the thing not to, so if you wanted this thing not to be massless, then indeed you want the transfer separation of these things. So what I'm giving you here is, roughly speaking, a T-dual picture of the story. So you should really mentally T-dual this picture, because what I'm describing is some kind of momentum excitations of the 5 grains. If you T-dualize it, the separation of the store strands becomes a B flux through this S2. And so you sort of have to mentally do your 5 T-dualities before breakfast and realize that there's some very natural interplay between duality frames. So this picture I was describing here, this is really the NS5P picture, where I have a bunch of momentum excitations that are puffing out the 5 grain in the transverse space. Okay, and that's related to the NS5F1 picture by doing T-duality along this circle. Okay, but the 5 grain is wrapping a direction which is not entirely parallel to nor transverse to that circle. So when I T-dualize along the Y circle, the piece of the 5 grain charge which is in this direction becomes KK monopole. And so when I then now say, okay, what's going on here is that there's some KK monopole structure that's degenerating, then I've mentally done that T-duality. And the separation in the transverse space is after that T-duality is the B flux through this 2 cycle. And so when I say the KK monopole cores are intersecting, I'm telling you that B flux is going to 0. Okay. Let me skip this. Right. So for the remaining time I have, which is 14 minutes, excellent. I'd like to tell you about a way of bolstering this picture by engineering the absence of the little string. So if I'm going to spin you some tale about how the non-perturbative excitations that I should be interested in that maybe are related to black hole entropy have to do with some kind of D-brain little strings that are wiggling around in the T4, then I can make all of that structure and all the entropy associated with it go away by taking away the T4. So,
why don't you want to backreact the fellows?
well, yeah, if I had control over non-perturbative string theory, I would do that. But I'm a perturbative string
We should
weakling.
only have the fibers on a screw to collapse. That's like in Lebanon cluster. We have the geometric transition.
Yeah, this is some kind of tensionless string transition.
But usually you get some Lebanon cluster. We know how this happens. We have an S2, the D5 is collapsing, the dual cycle becomes large. Then we have a clean geometry. So, in principle, we can go zooming on this thing and, probably next week we should sit down and, try to figure out. I think there's a way, there should be a way to zoom in on this thing and,
Maybe. I would dearly love that to be true. So let's make that a topic for discussion next week. Let's make that a topic for discussion next week. In the time remaining, I'd like to tell you about something complete, and now for something completely different, as they used to say. Yes. So I'm going to get rid of the T4. If I get rid of the T4, then I get rid of the entropy and wiggles, Hagedorn wiggles that are available to the little string. But you say, you should immediately ask me, well, how can you get rid of the T4? Doesn't string theory need to be 10-dimensional? And the answer is, of course not. I just have a collection of worldsheet signal models, and all I need to do is to engineer that the total central charge on the worldsheet is 10 bosonic and 10 fermionic degrees of freedom. Well, or more precisely, it needs to be a superconformal field theory of central charge 15, 3/2 of the bosonic. The bosonic central charge. So I can do that because the central charge of the worldsheet theory gets some contribution from ADS from SL2R, some contribution from SU2, some contribution from worldsheet fermions. I've taken away from T4, so I've gotten rid of the central charge 6 associated with the worldsheet T4. So I have to make it up somehow, and the way I make it up is by making K tiny. If I make K less than 1, this becomes bigger than 6, and it can become enough bigger than 6 that it makes up what I missed by taking away the T4. But what you need to do is you need to take the level of the SL2 less than 1, but the level of the SU2 is the radius of the ADS3 in string units. So we're working in some extremely stringy regime. It's thought that these models arise when you take the N5 fibranes and not wrap them around T4, but you wrap them around the vanishing 4 cycle of some non-complex Calabi-Yau 4-fold singularity. At least that was the interpretation given by these folks. And again, because the ADS radius in string units is coding where you are relative to some kind of correspondence transition, all of these models lie below the correspondence transition. So if you're below the correspondence transition, all of the entropy should be in perturbative strings, not in black holes. And indeed, that's true, as argued by these folks, that if you look at the high energy spectrum, there are strong arguments that it's dominated by perturbative strings. The winding strings that Andrea was talking about in his talk are in fact the dominant excitations at high energy. And another reason not to believe it is that we actually identified in work last summer that Bruno reported on in Black Hole Microstructure 3 that the dual space-time conformal field theory is a symmetric orbifold, but it's just a funny symmetric orbifold. Instead of being an orbifold, a symmetric orbifold where the block theory is the T4 that's wrapped by the fibranes, the T4 is now gone. So what do you have to make a symmetric product out of? Well, the remaining directions. And so the remaining directions are some directions in ADS3 cross S3. And it turns out the directions to choose are the radial direction in ADS3 and the angular directions transverse to the fibranes. The remaining R11s is basically the cylinder, the worldsheet of the spacetime CF. The coordinate domain of the spacetime CFT is 2 dimensions, and those 2 dimensions plus this R5 cross S3 is the thing that's dual to ADS3 cross S3. This funny subscript B is just because you have to squash. Well, actually, it's a musical flat, so it's just my joke that what you have to do is you have to squash the S3 until it's sort of maximally flat. So there's a flattened S3 times ADS3, that's the space-time geometry. But the important point is that the symmetric product now codes some structure of space-time transverse to the fibranes instead of along the fibranes. And moreover, what the symmetric product is describing is not some kind of little string structure, but actually the Fock space of Andrea's winding sector strings. Okay, but it's curious that we have 2 symmetric products in 2 different regimes. One of them is supposed to be a model for black hole microstates when I perturb away from the symmetric orbifold further away in the moduli space where the thing looks like supergravity. And the other of which is some slightly different space, but for which there is no black hole spectrum. Why do I say there's no black hole spectrum? I say it because this R5 that describes the radial direction has a linear dilaton. And anytime you have a linear dilettante theory, the SL2R invariant the would-be SL2R invariant vacuum state of this conformal field theory is not a normalizable state. So precisely when you go to this stringy regime, it turns out that the SL2R invariant vacuum is not a normalizable state in the space-time conformal field theory. Because it's not normalizable, the spectrum that it would be S-dual to in the Cartier analysis isn't there. So the BTZ spectrum is the thing that's related by torus space-time conformal field theory, tau goes to -1/tau duality. That's that the asymptotics of that spectrum is precisely related to the dimension of the lowest state in the conformal field theory. Because the lowest state is no longer the SL2R invariant vacuum, that black hole spectrum doesn't exist. What do you get instead? You get some spectrum which has a Carty-like growth, but with a smaller coefficient, where the coefficient is not the central charge, but it's the central charge decreased by the dimension of the lowest normalizable state that actually is in the Hilbert spectrum. And oops, not sure what happened. Okay, you're still okay. All right. So that minimum dimension is given in terms of the data of the theory. You can see that as you take the number of fibrates to infinity, you start to approach the Carty growth. But you never quite get there. Okay. As Andrea said, the theory that we're describing, well, it has a linear dilettante. So naively, you might say, well, then if there's nothing but the linear dilettante, coupling constant gets enormous. And so why am I describing to you a sensible theory? And the answer is that in the background, it's not really the linear dilettante theory. It's the linear dilettante theory perturbed by this particular operator, where sigma 2 is the Z2 twist operator of the symmetric overfold. And so this thing is a marginal operator. But it's this, the thing you should have in the back of your head is like Liouville theory, for those of you who know Liouville theory. The Liouville theory sometimes thought of as a linear dilettante theory with an exponential potential. And you could say, well, can't I just take away the exponential potential? The answer is no. The exponential potential is always there, and there's no way to turn it off consistently. And so similarly, the Z2 twist operator is always turned on in this theory. It represents string interactions. And because it has a profile in phi, what's happening is, and because the profile is exponentially growing one way, not the other, the direction phi goes to infinity, which is the asymptotic boundary of ADS, is the place where the string coupling turns off. So there's a self-consistent interpretation of these theories where there is in some sense, asymptotically free. As you go out to the ADS boundary, they become a Fock space of almost free strings. And as you go in towards the middle, the interactions increase. And the thing that in the space-time CFT mocks up the finite redshift cap of ADS is the fact that string coupling gets large there. And the collective interaction of an incoming probe string with all the other strings that are sitting in the background is such as to push them back away out to the weak coupling region. Just like you would say, take a long string, collapse it into the middle of ADS and expand it back out. Okay, and so, well, it's like any other asymptotically free theory. The coefficient of this thing isn't a coupling constant, it's a scale. I can always trade any coefficient for this operator by shifting phi. So there's just some scale in the theory in radius where the string interactions become order 1, and I should identify that with the middle of ADS. Okay, enough said, enough said. But the point I want to make is that because the high energy density of states is in one-to-one correspondence with the Fock space of perturbative strings, with some, oscillator excitations and winding ADS, the thermofield double of this system is just something where there is some, some fuzz of highly excited, thermally excited perturbative strings that's correlated with another copy. But there's no wormhole between them because, as I said, the BTZ solution, the black hole state, is not a normalizable part of the spectrum. So this thing doesn't exist. All that exists is this, some correlated gas of highly excited strings. So you could ask then about, you know, out of time order correlators, is there chaos, level statistics, blah, 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 blah. It's all very interesting. I have no idea how to compute any of it because we need to understand how to compute in the symmetric product deformed by this non-trivial interaction that you can't turn off. Yes?
Are you supposed to take this figure seriously because you are already not in a geometrical regime rather than a stringy regime?
Oh, this picture? Well, I mean, to the extent that the worldsheet theory is some SL2R Wessamino-Witten model, you know, in some sense, it is describing some kind of ADS3. It's just an ADS3 where the string scale is enormous relative to the ADS radius of curvature. So it's probably not best thought of as geometry. Remember, I said there were these two pictures of any SL2 representation, one of which looks like a graviton, one of which looks like a winding string. In this regime, the winding string piece of the wave function is always dominating, and the gravity piece of the wave function is always subdominant. So it's really better thought of in terms of a condensate of strings rather than in some kind of geometrical ADS3. Okay, there's a half Bps spectrum, which we calculated, which basically, it's interesting because if you try to look for normalizable wave functions, because the level is so tiny, all the graviton states are not normalizable. Part of this fact that the ADS vacuum itself is not normalizable is that every graviton you could think of is not, every graviton that has a bound state wave function, you know, decaying as you go away from the center of ADS, all of those are not normalizable. But there are half Bps states that come from the Ramon sector. And so there is, in fact, you know, again, some kind of counting that you can do of that spectrum, and there's a macroscopic number of them, and they would be interesting to study and scatter off of. But one thing I want to emphasize is that there's no missing fractionation of the momentum excitations. When you look at the quarter Bps spectrum, there was stuff missing from the enumerated elliptic genus in the T4 symmetric product, but none of that's missing here. So that fits. There are also supertubes. So this same game of gauge Wessamino-Witten models you can play just by throwing away the T4 and flattening the SU2. And did that with one of our postdocs, Daniel Brennan. Nothing too surprising. These things exist. Maybe you shouldn't take this geometry seriously, but anyways, it exists as a solvable worldsheet theory. But I should emphasize that because the graviton is not normalizable, you can't really think of this as a state in the theory you started with. It's some non-normalizable deformation, like the TT bar, right? TT bar changes the asymptotics, and it can't be interpreted as a new state in ADS3 conformal field theory. It's just some non-normalizable thing you turn on. This is like that. You can make supertubes that look like ADS3 cross S3 mod ZK, but they're not normalizable states in the theory you started with. There will, of course, be states you get by looking at the macroscopic condensate of the half Bps Ramon states. So it's like you could turn on 0,0 strands and make a Bps thing, but you couldn't turn on any plus strands. Okay. So just to summarize, I think I'm about out of time. Yeah. So I've been trying to propound a picture where I should think of ADS string theory in ADS3 as some kind of decoupling limit of little string theory holography on 5 branes. And so when you do that, then in these regimes where the number of 5 branes in the effective string theory is bigger than 1, so that I'm in a supergravity regime, then the thing you need to do is to find this factor of N5 in the fractionation of the excitation spectrum. And so far, I succeeded in doing that for the half Bps spectrum, but not for the quarter Bps spectrum. I speculated as to where the missing states might be. involving singularities that one might need to resolve involving coincident fibranes. And then showed you that I can provide a little bit of support for this picture by asking what happens when I take away the T4. And what I find is the black hole spectrum disappears. So that, if you like, is sort of, I don't know, evidence by absence. That maybe the fact that the black hole spectrum in the critical dimension has to do with little string theory excitations on T4. Well, at least it's evidence that the T4 should be important in understanding the black hole excitation spectrum. Let me just leave it at that. And thank you for your attention, and thank our organizers for a wonderful week.
More questions for Emil. Monica.
So you said that the graviton is not normalizable. I understand that your dual theory is symmetric, deformed symmetric for the orbit group. Does it have a stress tensor?
Yes.
But somehow when I try to construct my graviton,
sorry.
I'm acting with it on a normal relative vacuum or something.
I spoke too quickly. The graviton, the stress tensor doesn't exist for the same reason that the SL2 invariant vacuum doesn't exist. So Givon, Kuznetsov, and Seiberg tell you how to construct graviton vertex operators. When I say the SL2 invariant vacuum doesn't exist, the main piece of evidence for that is that Givon, Kuznetsov, and Seiberg in these SL2R string theories tell you how to construct the space-time Virasoro symmetry. And so in particular, for general central charge and ADS3 curvature and so on, they show you how to reconstruct the space-time stress tensor, the TT operator product expansion using the worldsheet. And so in particular, you can take the OPE of the stress tensor with itself and get the space-time Virasoro, TT makes C/4 times 1 over Z minus W to the 4th, et cetera. So there's an operator, there's a worldsheet operator you can identify as being the identity operator in the operator algebra of the space-time CFT. That identity operator, precisely when you go through this correspondence transition, becomes a non-normalizable operator. So the main evidence for one of the main pieces of evidence for the absence of the SL2R invariant vacuum is that the operator you would associate identity operator becomes a non-normalizable vertex operator in the worldsheet theory. And because it's not normalizable, the stress tensor, which is its descendant, is also not normalizable.
So I should somehow this theory should be understood in a very different sense from the normal way to understand that, DCT, where we can start how do you say axiomatically these are the opposites of CFT, blah blah.
No. So you have to be careful in the same way you have to be careful about Liouville theory. Okay, in Liouville theory, you have to be careful of. So usually in conformal field theory, compact target space, gapped spectrum, et cetera. There are a set of axioms, and one of the things there is a state operator correspondence. So there's an SL2R invariant vacuum, and then you look at the entire spectrum of scaling operators. Every scaling operator acting on the SL2 invariant vacuum makes some normalizable state. You're good to go. In Liouville theory, you have to decouple those two things. There's an operator algebra, and there's a spectrum of normalizable states, and they're not the same. So what I'm telling you is there is a stress tensor of the space-time CFT as a local operator in the theory, but there's no SL2 invariant state that thing acts on to make some kind of associated normalizable state in the Hilbert space.
That got me confused because your OP argument doesn't, apart from the fact that
it's just every vertex operator in that construction is not normalizable. It's just some wave function which is not decaying fast enough radially to be normalizable in ADS3.
maybe I can ask it.
Further question?
I have a question, not exactly related to what you are doing, but do you know of a string theory construction where instead of blowing up the S3 and taking ADS3 becoming small, it's the other way around? You take the S3 becoming smaller and smaller and the ADS3 blowing up?
That would be nice.
Yeah, well, yes. If you, yes, you can. You don't get much that way. So, so getting rid of the S3 means you're giving up the R symmetry. So you're talking, first of all, about some model with reduced supersymmetry in space-time. If you want control over the theory, probably you want to keep at least n equals 2. So maybe you want something like ADS3 cross S1 R symmetry times something. So that you can describe. It's something which will have a curvature of order the string scale, but a little bit bigger. So it's still very stringy, but it will have at least some spectrum of gravitons, some limited spectrum of gravitons that are normalizable, and you might try to think about holography with that. That's a class of models that was studied as a follow-up to the original Givon-Kudasov-Seiberg papers primarily by Givon. So if you look at the list of papers that cite GKS and they have Givon on the offer list, you'll come across basically the literature on the thing you're asking about.
Okay, one last one.
Yeah, maybe it's related to one of this question and comment. I think I know that here the supersymmetric level is less than 1, but bigger than 1/2. It's not like exactly 0.
No.
But I think some related issue is that it happens when you have the bosonic level, which is equal to the Coxeter number, In that case, you have the old tensionless case in which the Virasoro algebra becomes a bigger. You don't have an energy momentum tensor, and you still have the affine symmetry. In that case, you still have a consistent CFT, you just don't have the Virasoro energy momentum tensor, but there are mathematicians that are also using it for Lagrange duals and these kind of things. So I think maybe there is a way in which you can make sense of some CFT without energy momentum tensor. That's that regard. I know you have a level which is equal to 1/2, not 0.
Yeah, well, I think what I was trying to say and fumbled it a little bit is that there is an energy momentum tensor in these models. It's just you have to give up your usual intuition about how conformal field theory works. The usual intuition being that there's this one-to-one isomorphism between states and operators.
Right.
And any theory with a linear dilettante doesn't have that. And so if you think about Liouville theory, what do people calculate as correlators in Liouville theory? There's some exponentials e to the beta phi. And so you calculate, the 4-point function, the n-point function of e to the beta 1 phi, e to the beta 2 phi, et cetera. Most values of beta don't correspond to normalizable states. The e to the beta phi is just growing, exponentially in some direction. And if it's growing exponentially in the wrong direction, it's not a normalizable state. But it's a perfectly sensible perturbation. If you think about what is it that you want to calculate in ADS3 CFT2 duality? The holy grail is to calculate correlation functions of the space-time CFT. Those are some local operators, okay? So they're things that are localized at the boundary. So you're actually looking at vertex operators whose wave function is blowing up at the boundary. All the things that it's the standard, Witten GKPW correspondence. The things that are local perturbations on the boundary are non-normalizable gravity perturbations near the boundary of ADS3. So the fact that the stress tensor is not a normalizable operator is sort of standard operating procedure in the ADS3 CFT2 correspondence. Anything that's a local operator, its wave function is concentrated near the boundary where it's blowing up. So I don't think this should worry you that the stress tensor is not a normalizable operator.
Okay, thank you. So since this is the conclusion of week 1, and since many people will be leaving us, I propose that just before we thank Emil, we give one more round of applause for organizers, Nick and Joseph and Andre. And then let's give them more.